Okay, so do you see my screen?
Yes, we can see.
So let me briefly recall what we did on the last lecture. So we had a Gaussian measure on a separable Banach space X with the Borel sigma field B. We proved that polynomials of the form like a usual polynomial of a finite number of linear continuous functionals are dense in L2. Okay, we also defined a special Hermite polynomials H alpha, where alpha is a multi-index such that only finite number of indices are not equal to 0. And by xk, we denote the closure of the span of polynomials H alpha for which sum of alpha n is equal to k. And in this way, we obtained the representation of L2 space as a orthogonal sum of subspaces xk. And this representation is called the eta-Wiener expansion. Also, we noted that for let's say for continuously differentiable functionals, we have the following expression that the square of L2 norm of the derivative of f equals to the sum sum over k, k times, let's write it like this, norm ikf squared. Okay, where ik is a projection onto xk. And this equality allows to generalize the notion of continuously differentiable function on the abstract Banach space in the following way. So let D be the space of functions from L2 for which sum over k times norm ikf squared is finite. And for functions from this space, we can define some kind of an inner product, EFJ, as sum. Okay, we define it as 1/2 sum over k times the inner product of ikf and ikj. And well, this inner product is an abstract form of it's like the 1/2 the integral of the derivative of f times the derivative of g. And also we mentioned that this inner product E1, which is the sum of the inner product in L2 and E. So E1 is actually an inner product on the space D, and D is a Hilbert space with respect to the inner product E1. And also we defined the notion of a capacity of a set, which is for an open set U, the capacity of U, it is the infimum of E1 norms of all functions f from the space D that are greater or equal to 1 almost surely on U. And for any set A, the capacity of A, it is the infimum of capacities of open sets that contain A. Yeah, so also we noted that the measure gamma is always less than, the measure gamma of a set A is always less than the capacity of A. In particular, sets of capacity 0, they necessarily has a measure 0. But the converse, in general, it is not true. And we had an example that in one-dimensional case, the capacity of a point is not 0. So the notion of a capacity allows to look at finer properties of sets than the measure. Okay, and we formulated a number of properties of capacity. In particular, the first property states that the capacity of an open set actually it is attained on a unique function from the space D, such that this function is greater or equal to 1 on U. The function EU, which is also called equilibrium potential of U, it takes values between 0 and 1. Actually, it is equal to 1 almost surely on U. And we will also need this property 4 that states that E1 in the product of this potential EU with any function that is equal to 1 on set U is actually equal to the capacity of U. And now I will prove properties 5 to 7. Okay, so the property 5 states that if UN is an increasing sequence of open sets, then capacities of these sets, they increase to the capacity of the union. So let's consider equilibrium potentials EUN that corresponds to sets UN. And look at the inner product, look at the E1 norm of the difference, EUN minus EUM. Let's expand it. So here n is bigger than m. We will get E1, EUN, EUN, minus 2 E1, EUN, EUM, and plus E1, EUM, EUM. Okay, so the first term is the capacity of UN. And what is the inner product of EUN and EUM? Note that if n is bigger than m, then UM is a subset of UN, which means that EUN is equal to 1 on UM. And we had a property that for all such functions, their inner product with EUM will be equal to the capacity of UM. So it means that the second term is minus 2 capacity of UM. And the last one is plus capacity of UM. And then we get that actually the norm of the E1 norm of EUN minus EUM is equal to the capacity of UN minus capacity of UM. Okay, so sets UN are increasing, which means that capacities of these sets also increase and has a limit. So this converges to 0 when n and m converge to infinity. So it follows that in the space D, sequence EUN is a fundamental sequence. Yeah, then it has a limit. And actually, this limit, okay, so on each set UN, functions EU, they're equal to 1 for large enough indices, which means that I could write here that f that the limit f is also equals to 1 almost surely on the union of these sets. Right, and also we can know that if some function g is non-negative on the union of un, then it is non-negative on each set un, which implies that the inner product of EUN and G is non-negative. And in the limit, we will also have that this inner product of F and G is non-negative. And let me recall that the property that a function equals to 1 almost surely on U and has non-negative inner products with all functions f that are non-negative on U, it is actually it is a characterization of this equilibrium potential, which means that the limit of potentials EUN, in fact, it is a potential of the union. So capacity of UN, which is equal to E1 norm of EUN converges to E1 norm of FF, which is the capacity of the union. The next property 6, let's check that the capacity of the union of two open sets plus capacity of intersection is less than the sum of capacity of one set and the other set. So first of all, we know that EU1, if we take the maximum of potentials EU1, EU2, then this maximum will be equal to 1 on U1 and U2. Which means that the capacity of the union U1 and U2 is less than E1 norm of the maximum EU1 and EU2. In the same way, if we take the intersection of EU1 and EU2, it will be equal to 1 on the intersection of U1 and U2. Which means that the capacity of the intersection is less than E1 norm of EU1 minimum EU2. So I wrote it a little bit incorrect. So here I should have E1 of maximum and the maximum plus E1 of minimum and minimum. Okay, now we can use the following property that the maximum equals to 1/2 of the sum plus absolute value of the difference. Okay, and minimum equals to 1/2 of the sum minus absolute value of the difference. Okay, so this expression, if we use these two, if we use representations for maximum and minimum, we will have that this expression equals E1 1/2 sum and the same expression here plus E1 of 1/2 sum minus absolute value of the difference. And now let's expand this by linearity of E1 in each argument. We will have twice, we will have 1/4 E1 of the sum, which will be this term. And we will have twice twice 1/4 E1 of the absolute value of the difference. And the cross terms will cancel because in the first inner product we have the sum, yes, and in the second we have the sum of E1 EU1 plus EU2 and absolute value of the difference. And in the second, we have the difference of the sum, EU1 and EU2, and absolute value of the difference. Okay, now also let me recall that contractions decrease the inner product E1. Which means in particular that the inner product E1 of absolute value of okay, so E1 norm of absolute value of the difference EU1 and EU2 is less than E1 norm of the difference EU1 and EU2. Okay, so we get the estimate in the third line. And now again, if we expand the inner product, we will have twice 1/2 in the product of EU1 and EU1, which is the capacity of U1. Also, we will have twice E1 norm of EU2 times 1/2, which will give us the capacity of U2. And also the terms like E1 product of EU1 and EU2 will disappear, because in the first summand we have the sum of EU1 and EU2, and in the second we have the difference of EU1 and EU2. So we have that the capacity of the union plus capacity of intersection is not bigger than capacity of one set plus the capacity of the other set. In particular, capacity of the union of two sets less or equal than the sum of capacities. This can be also extended to any finite number of sets. Okay, and since we have the property number 5, actually this can be also extended to a sequence of sets. So if we have an infinite sequence of sets, let's say CU1, CU2, okay, then the capacity of the union of this infinite sequence, it is a limit of capacities of unions of finite number of sets, which will be not bigger than the sum of capacities of sets from this sequence. Okay, and this sub-additivity allows to prove a variant of the Borel-Cantelli lemma, which is the property number 7. So if AN is a sequence of sets such that the sum of capacities is finite, then the upper limit of this sequence has a capacity 0. Okay, so let me probably recall what is the upper limit of a sequence of sets. It is a set of points x such that x belongs to AN for infinitely many indices n. And it also can be written as follows. So it is an intersection over n of the union when k changes from n to infinity, ak. This last expression means that for all n, we can find a larger index k such that ak contains x. So this is the same as to say that x belongs to infinitely many sets an. Okay, so now assume that the sum of capacities of sets A is finite, then the capacity of upper limit it is equal to the capacity of intersection over n of the union k changes from n to infinity ak, and okay, so the intersection is smaller than any set from this of this form, and the capacity of the union is smaller than sum of capacities of ak. And now, since the sum of capacities of an is finite, is assumed to be finite, when we take sum from n to infinity and take the limit when n goes to infinity, this will go to 0. Okay, so now using these properties of capacity, we can consider one interesting example. So first of all, if we have some property of a point x, we say that it holds quasi everywhere if it holds outside a set of capacity 0. It's like an analog of the property that holds almost surely. We say that px holds almost surely if the set of points where px fails has measure 0, and we say that px holds quasi everywhere if the capacity of the set of points where this property fails is equal to 0. In particular, a property, if some property holds quasi everywhere, then it holds almost surely. But as we saw, the converse is not true. So again, if we know that some property holds quasi everywhere, then it is a much stronger statement than to say that it holds almost surely. Okay, so to prove that some properties holds quasi everywhere, there is a simple estimate. If we consider a continuous function from the space D, and consider a set where it is where this function is bigger than a number lambda, then the capacity of this set is estimated by the following. So this is 1 over lambda squared times E1 norm of the function f. Indeed, so this is an open set, and if we take absolute value of f and divide it by lambda, then this function will be bigger than 1 on the set U. Yes, because on the set U, f is bigger than lambda, so f over lambda will be bigger than 1. Then the capacity of U will be less than U1 norm of f over lambda. Okay, then we take outside lambdas. Yes, we get 1 over lambda squared. And also recall that contractions decrease the E1 norm, which means that this is less than lambda minus 2 E1 of f and f. Okay, so we have such estimate of the capacity. And now let's look at interesting example of a property that holds quasi everywhere. So let W be a Brownian motion. Gamma W is the distribution of this Brownian motion in the space of continuous functions. Let's consider a sequence of partitions of the segment from 0 to t. So delta n is a partition that consists of points tn1 till tn, well, some number of points. So here we assume that tn0 is 0, less than tn1, and so on, tnmn, which is equal to t. Okay, so we have such sequence of partitions. By absolute value of delta n, I will understand the size of the partition. So this is the largest difference between two consecutive points. And let's take these partitions in such a way that the sum of absolute the sum of sizes of partitions is finite. Okay, for example, we can take partitions of the kind like kt divided by 2 to the power n. Okay, so next we for each partition we consider the sum of increments of the Brownian motion squared. which is also known as yeah, okay. So and one of the basic properties of the Brownian motion is that this sum of increments squared converges to t almost surely. But in fact, we have a much more stronger statement that the convergence is not only almost surely, but the convergence is quasi everywhere. So, this property is also known as quadratic variation of the Brownian motion. So now let's check this property. Let Sn be the sum of squares of increments of the Brownian motion. And let's look at the difference between Sn and t. So note that if we take the sum of just differences between tnk and tnk minus 1, so this is just the sum of lengths of elements of the partition, which gives t. So Sn minus t can be written as the following sum. Now let's look at summands. So each summand in this sum, it is actually a polynomial from W of degree 2. Moreover, it is actually, if we take outside tnk minus tn k minus 1, then in brackets we will have wtnk minus wtnk minus 1 divided by root of tnk minus tnk minus 1 squared minus 1. And here we can note that actually this is the second Hermite polynomial applied to this function. In other words, we get exactly the sum, which is an element of the space of orthogonal polynomials of degree 2. In particular, the projection of the difference Sn minus t on a space xk, it is equal to 0 when k is not equal to 2, and it coincides with Sn minus t when k is equal to 2. Now let's look at the E norm of the difference Sn minus t. It is by definition the sum of k norm of ik of Sn minus t squared. Okay, but we find all these projections. So in this sum, the only sum and that remains corresponds to k is equal to 2. So this is Sn minus t squared. Next, we can find E1 norm of Sn minus t, and it is equal to L2 norm plus E norm. Yes, so it will be equal to 2 L2 norm of Sn minus t squared. So this is 2 times expectation of the sum of increments of the Brownian motion squared minus tnk minus tnk minus 1 and expectation squared. Now let's note that actually the expectation of the increment of the Brownian motion squared equals to tnk minus tnk minus 1. This means that actually from this sum of these squares, we subtract its expectation and then take the square and expectation. Yes, so this is just the variance of the sum of increments of the Brownian motion squared. Okay, now we can use the property that consecutive increments of the Brownian motion are independent. So the variance of the sum equals to the sum of the variances. And one more property, that the increment of the Brownian motion in distribution, it is the root of the root of the length of the interval where we take increments times the standard normal variable. Okay, so when we take the square, we so the root disappears, and then we can take outside the difference tnk minus 1 from the variance, and it will give us tnk minus 1 squared. And what remains is a constant, which is just the variance of the standard normal variable squared. Okay, and uh, the last estimate is instead of differences squared, write it as a product of two differences and estimate one of them by the size of the partition. Then the sum of what remains will give just t. So now let's consider the capacity of a set where Sn minus t is bigger than some fixed number lambda. We have an estimate that such capacity is not bigger than 1 over lambda squared E1 Sn minus t, which is, we estimated it as 2c over lambda squared times t times the sum of sizes of partitions delta n. And we had an assumption that this sum is finite. Okay, so the sum of capacities of these sets is also finite. And by the capacitary version of Borel-Cantelli, the capacity of sets of realizations of the Brownian motion such that Sn minus t is bigger than lambda infinitely for infinitely many indices. Infinitely many n's, this capacity is equal to 0. Now let's, instead of lambda, take, let's say, 1 over k, and take the union over k. Again, we will get a set of capacity 0, and outside this set, for any k, for all large enough n, the sum of squares, squares of increments minus t will be less than 1 over k. Which actually, it means that outside this set, Sn converges to t. Okay, so this gives like a finer understanding of the existence of quadratic variation of the Brownian motion. And maybe the last thing that I wanted to say is that if we consider a dual space to the space D. So this is like the space of linear continuous functionals on D. Then if this functional is non-negative, there is a theorem by Sugita that the action of this functional can be represented as an integration with respect to some measure nu. And it can happen that this measure is singular with respect to initial Gaussian measure gamma. However, this measure nu doesn't charge sets of capacity 0. In this way, properties of the measure gamma that holds not only almost surely, but that holds quasi everywhere, they can be transferred to distributions, to some distributions that are actually singular with respect to the measure gamma. One such example is Brownian bridge. Brownian bridge. So this is a process whose distribution is singular with respect to the distribution of the Brownian motion. However, it has all properties of the Brownian motion that hold quasi everywhere. Okay, so maybe that's all what I wanted to say today. So thank you for the attention. Maybe there are some questions or comments.
Okay, so thank you for your lectures, and so that was the last lecture by Riabov, and but now we will have one more lecture, so we will have a break of 13 minutes before our next lecture. No? That's right.